Hi, and welcome to this Engineering Mechanics lecture video. Let me share my screen and we'll get started. Okay, so in this lecture video, we're going to build on what we learned in the previous two lecture videos, where we looked at the moment of a force and then the moment of a couple. And now we're going to look at equivalent force couple systems or equivalent force moment systems. So our objectives for this lecture are for you to firstly determine the effect of moving a force, and then secondly to find an equivalent force couple system for a system of forces and couples, or just a system of forces. So like we've got shown here, right? So here we've just got a crane, workshop crane, and we've got 1, 2, 3, 4 forces here. So something that we might want to do if we're having to design this or install it is to work out how many and what size bolts we need down here at the support. Okay? And when you get to later subjects where you do those kinds of calculations and those kinds of detailed design problems, usually what you need to do is to find out the normal and tangential force or shear force and the moment that's applied at this location when you're calculating these bolt loads and the size of the bolts that you need. Okay, so what we're going to do in looking at equivalent force couple systems is to find an equivalent force or forces and moment or couple at point A. So we can just find an equivalent single force, but as I said, usually in a practical problem like this, what we actually want to do is find the normal and shear force. Anyway, you'll see that hopefully in the lecture and also in the example problems that we look at later. All right, so thinking about what happens when you move a force when you've applied it to something. All right, so I'll keep my screen small, so hopefully you can see me still up in the corner here. So in the top picture, if we have something like this held at one end and we apply a force and pull at the other end, and we compare that to what happens if we apply the force right next to the support, right? There's no real difference in what I need to do in my left hand, right? So if I pull over here, or if I pull right next to my hand, right, the force that I need to apply here to stop the stick from moving is the same, okay? However, if I apply a force here, downwards, if I apply the force here, I can just have my thumb. Right? So if we work back the other way, right? So if I apply the force downwards, I can just have my thumb underneath to resist that. But if I tried to move that force out now, right, clearly you know that that's going to just rotate and fall off the support here. Right? So in moving the force from here out to here somewhere, right, I've had to do something different at the support end of the stick, right? Sorry, I was looking slightly away from the camera. I'm looking at myself rather than at the camera. Yeah, so if I want to have an equivalent force hit close to my hand to what I've got out here, then I must have a force and a moment applied for that to be equivalent, right? So I can have just a single force out here, but if I want to have an equivalent force and moment somewhere else, I need to apply a force and a moment here. When you looked at forces previously, you knew that you could slide a force along its line of action, right? So it's known as a sliding vector, but you can't move the force off its line of action, okay? And this also goes back to, you know, in some of my previous video lectures and example problems, when you draw your components, right? So just for those of you who haven't seen that, let me just do that again. Right? If you've got a force up here like this, and I tell you to draw the components, quite often what a student will do is say, we've got that, and then we've got that as its components. Right? Now, that's not necessarily wrong, okay, but it can lead to misunderstanding and lead to you thinking wrongly about what you do next. Okay, so I much prefer that when you draw components, and I always draw components like this, so that I maintain the line of action of the force, right? So that when I go to calculate moments, and I'm using the components of a force to calculate moments, the components are at their correct line of action, right? And I can work out the correct distance to the point that I wanted to calculate moments about. Okay, so this is just a picture from the textbook that shows graphically what I was just talking about. Okay, so here we start off with a force. If we apply forces equal and opposite at some other point, okay, so here's our original force F. If we apply another force of the same magnitude in the same line of action, and then another force of the same magnitude but opposite in sense, right, then we've essentially done nothing, right? So this force here is equal and opposite to this force. So you can hopefully clearly see that this is equivalent to what we had originally. Right? We've got the original force here and these two new forces. But if we get rid of this one and this one, right, we're left with this force here that's slided along. Right? So here we can see that this force here is equivalent, or this system of forces here is equivalent to the one we had here. Right? So that's just your sliding vector. Force is a sliding vector that you've seen before. Okay, so this is written down what I've just explained. Just in terms of the internal effect, so again, if we go back to looking at the internal effects of this, and previously in the previous video, we looked at the fact that a couple is a free vector and we can apply that couple anywhere we like, and it doesn't change the external effect on the body. Okay, but it does change the internal effect. So if you can imagine, if this was an elastic band, for example, if I apply the forces like this, it's going to stretch. Yeah. Whereas if I apply the force here, you only get a little bit of stretch, and the rest of the elastic band just flops down. Yeah. Right? But the force that I need to hold in my left hand to balance the force that I'm applying in my right hand is the same whether I apply the force here or whether I apply it out here. Right? So the external effect's the same, but the internal effect is different. Right? So here I get a stretch of the rubber band. It's going to stretch it out, whereas here it just stretches this little bit and the rest just flops down. Yeah? Now, moving a force off its line of action. Okay, so this is doing the same thing again. So we've got a force here, but instead of applying the force at point O in the same direction as A, we've got these two equal and opposite forces applied somewhere off the line of action. Okay, so applying a force here at the same location, equal and opposite, we've effectively done nothing. Right? But if we look at these two forces here, we can see that they're separated by a distance, parallel, equal and opposite, separated by a distance. This is going to cause a moment or a couple. Right? So here, moving the force off its line of action to get an equivalent system, we need to have a couple associated with this new system. Okay, so on the previous page, we had a force. The equivalent system was just another force at another point, but along the same line of action. Here, we've got a force equivalent to this one, same magnitude and direction, but off its line of action. For this to be equivalent, we need an associated couple or moment. All right, let's simplify that a little bit in a second. All right, so as we discussed before, a couple is a free vector, so we can apply this couple anywhere. So we've said it's at point P here, can be anywhere we like. Okay, so here, with our force acting at vertically downwards on this ruler, the equivalent system, if we have a force over here, is that we must have this moment or couple associated with that. Okay, so now we can use our knowledge of couples to move from a couple and a moment, or a couple and a force to a force only, or a force to from a force to a force and a couple, and so on. So as I explained at the start of the lecture, the reason we might want to do that is because we want to know the equivalent force and moment or couple at the base here. Right, so if we keep it really simple and look at the process by which we do this, we start with just an original force F, okay, applied to some beam that's supported. So similar to here, what I had, we've got supported at one end and we're applying a load at the other end. If we place two equal and opposite and collinear forces the same magnitude as our original force, right, so we've done same force acting downwards and the same magnitude force acting upwards at the same point. So this minus this equals 0. So we've effectively done nothing, right? And if we put these two forces here at some distance away, A, then we can recognize that this force here, our original force, and one of these two forces that we put here at distance A away form a couple. So if we replace this couple, or these two forces here that form a couple, with the arc with an arrow on it that represents a moment or a couple, equal to force times the distance between them, right? So the magnitude of our couple, this is now equivalent to what we had before, right? In terms of external effects. Now going back the other way can be just as valid and useful. Okay, so we can start off with a force and a moment, or a force and a couple, and find the equivalent single force somewhere, right? And there'll be some example problems and some tutorial problems where you need to do that. So I'm not sure what the next slide has got. No, it doesn't have that. So imagine we don't have this left-hand side of the screen here, and you've got a problem that says you've got a force and a moment acting on some structure, or a force and a couple. Find the equivalent system where it's just a single force, right? So you need to work out the location. All right, so from the textbook, if you've got more than one force, the process is just more of the same, okay? So here, if you want to find the equivalent force and moment at point A, at the hand support here we've got two forces, F1 and F2. We just sum up all of those moment effects of each of those forces. So we just use the scalar equations. So we've got the two forces. In this case, we've only got forces acting vertically downwards. If we had the problem like we had before with the crane, the workshop crane, we had a force at an angle, right? So we'd need to do both force in the y direction, as we have here, plus force in the x direction, right, to get the resultant forces. And then we also need to find the resultant moments of those forces that are applied. Okay, so in general, calculate the moments about some point. Right, here it was A. Here I've just said in general about some point O. And then you may also have some examples where you've got an applied couple or an applied moment that you need to add in as well. Okay, so in textbooks, right, you'll often see problems like this with applied moments or couples. So actually, when you look at problems that in the textbook, when you have something like this drawn on them, you should think of these as applied couples. Okay. So if you're going to draw a free body diagram and try to solve the reaction forces for this problem, which we'll do in the next topic when we look at rigid body equilibrium, think about how are you going to deal with this 600 Newton meter couple or moment. Right? So what I see a lot of students mistakenly do is to put a force somewhere, okay? But you can't do that, right? The only way you can do that is because this is a couple. What's this equivalent to? it's equivalent to, if I go back to my drawing, right, it's not equivalent to some force here, right, some single force. It's equivalent to a couple of forces. Okay, so if this was 600 newtons, right, so if these two forces were 600 newtons, what's the distance between, whoops, undo, what's the distance between them going to be? Right, 1 meter, right? Okay, so we don't actually need to draw that in our analysis, right? We can simply, if I go back to the previous page, we just need to add in the moment in our equation here. Okay, so these ones will have some F1 times B1 plus F2 times D2, etc. But if there was if we also had a, like in those problems that I just showed you, if we also had a moment here, some moment applied or couple applied, that would go into here, and we just have the value of this. Whereas these guys go into that. Right? Okay, so just, yeah, don't worry too much about these pictures. The main thing I want to show you here is that you're going to come across problems like this, and the way to think about these applied couples or applied moments, as they may be described in the question, is that they're a couple. Okay, so they're the two forces, equal and opposite, separated by a distance. Okay, so that's it for this lecture video. See you in the next one. Bye for now.